Welcome back to the deep dive. Today, we're really digging into something that's just exploded: prompt engineering. And look, if you're still thinking it's just about, asking better questions to an AI, well, things have moved on quite a bit, actually. It's really evolving into a proper engineering discipline, much more systematic than you might think at first glance. Imagine you're trying to build something complex, right? Like a customer service AI. Needs to be personal, needs up to the minute info, understand really tricky questions, maybe connect to your CRM. That's the kind of heavy lifting prompt engineering is tackling now. So for this deep dive, we've pulled some key ideas from Mastering Prompt Engineering and LLM Operations, and also the Developer's Guide to Production Grade Prompt Engineering. Our mission for you listening in is to cut through that complexity. We want you to grasp the structured, systematic approach that really unlocks what these large language models can do. We're aiming to shift this from feeling like some kind of dark art into a core engineering skill, something that equips you to build robust, real-world AI solutions. So, okay. If asking better questions was maybe prompting 1.0, what does this next stage, this prompting 2.0, actually look like in practice? Yeah, it's definitely less about just kind of crossing your fingers and hoping for the best. It's much more structured. It blends that technical know-how with some creative problem solving. That's what makes it feel like engineering, I think. And right at the heart of crafting these professional grade prompts, we often find something called the core framework. Core, okay, what's that stand for? Right, so it's CORE, context, objective, role, and then exemplars and constraints. Let's maybe break those down a bit. Context. That's about giving the background, right? So like for that customer service agent example, it could be the user's purchase history, maybe their last couple of emails. Just giving the AI the relevant facts it needs for this specific situation. Makes sense. Then objective dot or task. That sounds straightforward. It is, but it needs to be precise. Clearly define what you want the model to do, not just help the customer, but maybe summarize the support ticket into 3 bullet points or generate Python code to analyze this customer data. Got it. And role. That sounds interesting. Giving the AI a persona. Yeah, and it's surprisingly powerful. You might say, act as a senior customer support specialist with 10 years experience in software issues. That helps guide the AI to respond with the right level of expertise, the right tone, empathy even. Okay, I can see how that would shape the output. And the last one, exemplars and constraints.
Yep.
Exemplars just means giving examples, like here's a good answer, or here are a couple of good answers. That's often called few-shot prompting. And constraints are the rules, things like respond in JSON format, keep it under 50 words, don't mention competitor X.
It's fascinating, isn't it, how these foundational techniques really shape the guidance you bake right into the prompt. And we usually talk about this in terms of zero-shot, one-shot, and few-shot prompting. It really depends on how much example data you give the model to learn from in that moment. So zero-shot, the model's just using its pre-trained knowledge. Everything it learned during that massive training phase is generally pretty good for broad tasks. Simple sentiment analysis, like, is this review positive or negative? Or maybe a direct translation. Things the model likely saw millions of examples of during training. The big pluses: it's fast for prototyping. You don't need to prep any specific examples, just write the prompt and go. But the downside, well, it can be less accurate for really niche or totally new tasks. And you have less direct control over let's say, the exact style or format of the output. Okay, so that's 0 examples. What about one shot and few shot? Right, so here, you actually put one example, one shot, or maybe, 2, 3, 5 examples, few shot, directly into the prompt itself. You're showing it.
Given an input like this, I want an output like that. It's a form of what we call in-context learning. The model adapts its response based on the examples you provide right there in the context window. And this is where you get much better results for novel tasks. Or when you absolutely need a specific format like perfectly structured JSON, or if you need to control the style very precisely, maybe make it sound very formal or very casual, the upside is usually, yeah, much higher accuracy, much more control. The cons, well, you need good examples, high quality representative examples. And there's always a bit of a risk of overfitting. If your examples are too narrow, the model might struggle with inputs that look a bit different. So ultimately, choosing between them, it's a trade-off, isn't it? You're balancing the sort of ease and speed of zero shot against the control and accuracy you get with few shot. And it really depends on the task and whether you even have good example data available.
Okay, so we've got these foundational core principles and the idea of 0, 1, or few shot examples. That gives us a good starting point. But let's be real, right? Real world problems, maybe they're messy. They aren't usually just one simple question. What happens when the AI needs to actually reason through something, or maybe even fetch information from outside its own knowledge, like for that complex customer query.
Right.
Yeah, this is where things get really interesting, I think. It leads us to more advanced patterns. And one of the first big ones people latched onto was chain of thought prompting, CoQT. Chain of thought, like showing your work in math class, exactly like that. Instead of the AI just jumping straight to the final answer, you prompt it in a way that encourages it to break the problem down, to think through the intermediate steps logically, one after the other.
Precisely. And it makes a huge difference. We see significantly better performance on tasks that require reasoning, arithmetic, yeah, but also common sense stuff, logical deduction problems. And crucially, it's not just about getting a better answer. It makes the model's reasoning transparent. You can actually see how it got there, and that transparency, it's not just for debugging, though that's useful. It starts to shift the AI from this sort of inscrutable black box into more of a collaborative partner. You can see its thought process, maybe even correct it if it goes off track, like reviewing an engineer's calculations or design steps. You can trigger this in a couple of ways. There's zero-shot caught. Often just adding a simple phrase like, let's think step by step to the end of your prompt can be enough. Or for more complex things, you might use few-shot copy, where you provide examples that explicitly show that step-by-step reasoning process.
Okay, that's clever, getting the AI to lay out its logic.
Mhm.
But what if that single chain of thought, even if it's detailed, has a mistake in it somewhere? One wrong step could mess up the whole answer, couldn't it? Especially for something critical like that customer service system.
Right. That's a really important point, a very real risk. And to address that, there's another technique called self-consistency. It builds directly on chain of thought. But instead of generating just one reasoning path, you ask the model to generate multiple different paths. Maybe ask it to approach the problem from slightly different angles, or just run the same CoT prompt several times with a bit of randomness enabled. Then you look at all the final answers produced by these different reasoning chains, and you essentially take a majority vote. This makes it much more robust. A single flaw in one chain is less likely to lead to the wrong final answer. It's like having a small committee of AIs checking each other's work. Boosts reliability quite a bit. And there's even an extension called Universal Self-Consistency, or USC. For more subjective tasks where a simple vote isn't quite right, USC can use another powerful LLM as a kind of judge to evaluate the different reasoning paths and outcomes, adding another layer of nuance.
Okay, so CoT helps it think internally, step by step. Self-consistency makes that thinking more robust. But what about the AI's knowledge cutoff? Its training data is frozen in time, right? So if our customer agent needs to answer a question about, say, today's stock levels, or maybe a policy change that just happened an hour ago, it can't just think its way to that new information, can it?
Yeah, exactly. That's a fundamental limitation for dynamic, real-world applications. And that brings us to the React framework. React stands for reason plus act. Think of it like this. You've got this incredibly smart librarian, but they're stuck in a library where no new books have arrived for months. They only know what's already on the shelves. React teaches that librarian a new process. First, think about what specific piece of information is missing to answer the current question. That's the reason or thought part. Then, critically, go out and do something to find that missing info. That's the act part. This action might be querying a search engine API, looking something up in a company database, checking an inventory system via an internal tool. After taking the action, the AI gets back a result, the observation. It reads that new piece of information. And then it combines its internal knowledge with this fresh external observation to generate the final up-to-date answer. This whole loop, thought, action, observation, thought, allows the AI to dynamically retrieve and incorporate real-time information. It leads to much more factual responses and fewer instances of the AI just making things up, which we call hallucination.
That makes a lot of sense for staying current. Now, thinking about integrating these AI responses into actual software, like our customer tool, we often don't just want paragraphs of text. We need structured data, right? Like maybe JSON or XML output so other parts of the system can easily understand and use the AI's response. How do we make sure we get that reliably?
Yeah, that's a really practical challenge, just telling the model respond in JSON format. Well, it tries, but it can be brittle. It might forget a comma, use quotes wrong, put a string where a number should be, breaks the downstream system. A much more robust way is to actually use structure within the prompt itself to guide the model more clearly. For instance, using XML tags within your prompt to clearly separate instructions, provide context, and specify the exact output structure you want. That can make the task much less ambiguous for the LLM. And beyond that, frameworks like LangChain offer tools called output parser classes. There's an XML output parser and things like Pydantic output parser, which is great for enforcing JSON schemas defined using Pydantic models. These parsers do two key things. First, they often help format the prompt itself to include clear instructions about the desired output schema. And second, crucially, after the LLM generates its response, the parser attempts to parse that output and validates it against your defined structure. If it doesn't match, it can even try to fix it or at least flag the error. That's absolutely vital for building reliable production pipelines.
Okay, so it really sounds like prompt engineering isn't this one and done thing. You don't just write the perfect prompt on day one and walk away. It's much more iterative, right? Like any proper engineering process.
Absolutely. Iterative refinement is totally key. It turns what can feel like guesswork, like just trying random things, into something more like a measurable science. You can think of it as a continuous loop. You prompt, then you evaluate the output, you analyze what worked and what didn't, and then you refine the prompt based on that analysis. And then you go again. The general idea is often to start fairly broad with your initial prompt, see what the model does, and then systematically narrow it down, tune it, optimize it based on the results. Every output, even if it's completely wrong, is valuable data. It tells you something about how the model interpreted your instructions and gives you clues on how to tweak the prompt for the next iteration.
So can you give us some concrete techniques for that refinement step? Beyond just vaguely saying be more specific, how do you actually hone these prompts in practice?
Yeah, definitely. There are several specific things you can try based on what you're seeing in the output. If the logic in the AI's response seems weak or flawed, you can actually prompt the model to critique its own argument. Ask it to identify weaknesses and then rewrite it to be more sound. To improve clarity, you can explicitly instruct it to target a specific audience, like rewrite this technical explanation for an 8th grade reading level, or explain this concept as you would to a marketing manager. If you need it to be more persuasive, maybe for sales copy or something, you can ask the model to anticipate potential objections or counterarguments and address them directly in its response. For accuracy, if you have newer information, you can provide that information and explicitly instruct the model to update its previous response, correcting any inaccuracies. And a really interesting meta technique is called reflection prompting. You basically ask the AI to evaluate its own response against a set of criteria you provide, like rate your previous response on clarity, conciseness, and tone from 1 to 5 and explain your rating. This forces a kind of deeper self-assessment.
That sounds incredibly useful. And it feels like this whole iterative process, focusing on the quality of the output, it must tie directly into the user experience, the UX, right? How does better prompt design actually make things better for the person using the AI tool?
Oh, absolutely. The connection is direct and profound. Thoughtful prompt design is UX design in many ways for AI applications. By tailoring outputs for different user personas, a tech expert needs different details than a novice user, we make the information more relevant and helpful for that specific user. It also affects accessibility. You can prompt the AI to suggest ways to make content more accessible for, say, visually impaired users, or to summarize complex charts into simple text descriptions. And maybe most importantly, that iterative refinement loop is crucial for ensuring the AI is consistently helpful, harmless, and responsible. It helps you catch and fix prompts that might lead to biased, misleading, or just unhelpful outputs. That's fundamental for building user trust and delivering a positive experience.
So, okay, we're iterating, we're refining, but how do we know if we're actually succeeding? What does success look like in prompt engineering, especially when we need to build production-grade AI? It feels like we need to move beyond just a subjective, yeah, that seems better. How do we measure this stuff?
Right, measurement is critical. And we generally use a mix of approaches. For getting quick feedback, especially at scale or early on, we often rely on automated metrics. You might have heard of things like BLEU, Rouge, or Meteor. These are often used for tasks like translation or summarization. They basically work by comparing the AI's output text statistically to one or more human-written reference or gold standard text. How much word overlap is there? Stuff like that. Or there's perplexity, which kind of measures how surprised the model is by the sequence of words it generated. Lower perplexity generally means higher fluency. It fits statistical patterns of language better. The pros. These metrics are fast, they're cheap to run, and they scale really well. You could evaluate thousands of outputs quickly. The cons, though, they're pretty surface level. They measure statistical similarity, not deep semantic understanding or creativity or helpfulness or factual accuracy sometimes. An output could get a great BLEU score but still be subtly wrong or nonsensical to a human. So useful, but definitely not the whole story.
Okay, so automated metrics give us a quick signal. But what about tasks where the quality is more subjective, or where human judgment is really needed to say if it's actually good?
Yeah, for that, human-in-the-loop evaluation, or HITL, is still considered the gold standard for capturing nuance and true quality. This just means getting humans involved in assessing the outputs.
It could be through simple rating scales like rate this response from 1 to 5 on helpfulness, or user surveys asking about their experience. You can run A/B tests, where you deploy 2 different prompt versions to different sets of real users and see which one performs better on key metrics. Or you might have subject matter experts review the outputs for accuracy and relevance. The big advantage here is you're getting direct feedback on what actually matters to humans. Much higher fidelity for assessing true quality. The downsides are pretty obvious, though. It's slow, it can be very expensive, and you have to worry about consistency between different human raters. Training and calibrating raters is a whole task in itself.
Right. Slow and expensive. Is there anything in between? Something faster than humans, but maybe smarter than just BLU scores.
Yes, actually. There's a really interesting and increasingly popular approach called LLM as a judge. The idea here is to use another, usually very powerful large language model, think something like GPT-4 or Claude 3 Opus, to act as the evaluator. You give this judge LM, the original prompt, the generated output from the model you're testing, and a carefully crafted rubric or set of criteria. Then you ask the judge LLM to score the output based on that rubric, the pros. It can be significantly faster and cheaper than manual human review, especially at scale. And it allows you to get qualitative evaluation, judging things like coherence, relevance, safety in a more scalable way. The cons. Well, these judge LLMs can have their own biases. One known issue is position bias, where the judge might unfairly favor the first or last option presented to it, regardless of quality. So designing the prompt for the judge LLM becomes really critical to get reliable results. It's a powerful technique, but needs careful implementation.
Okay, this is fascinating. We're talking evaluation, iteration.
Right.
This feels like it's moving squarely into managing these prompts in a real production setting. Which leads us to LLMOps, right? Large language model operations. Sounds like a specialized field within the broader MLOps world.
That's exactly right. LLMOps is emerging as a crucial specialization within MLOps, tailored specifically for the unique challenges of working with large language models. The core idea is to treat prompts not just as bits of text you tweak, but as critical, executable components of your software system. They need to be managed with the same rigor as your application code. This is especially important because, as we touched on, LLM outputs can be non-deterministic. The same prompt might give slightly different results each time you run it. That adds a whole layer of complexity to testing, validation, and monitoring that traditional software doesn't always have. LLMOps provides the frameworks to handle that. So why is LLMOps so important? Well, several key reasons. First, basic version control for prompts. As applications grow and teams collaborate, you absolutely need a way to track changes, revert prompts, compare versions. Otherwise, it's chaos. Second, handling that non-deterministic nature. LLMOps include practices and tools for robust testing and validation, specifically designed for probabilistic outputs. Then there's ongoing performance monitoring and production. You need to track not just basic things like latency and cost, token usage, but also the quality of the outputs over time. You need to watch for drift. Maybe the underlying data distributions change, data drift, or the meaning of your data embeddings shifts subtly, embedding drift, making your prompts less effective. And of course, monitoring for safety, bias, and harmful content generation is critical. And finally, LLMs platforms help with scalability and collaboration. They provide centralized places to manage prompts, share best practices, and standardize workflows across teams.
And presumably, specific tools are popping up to actually do all this. It's not just managing text files in Git, I imagine.
Oh yeah, the ecosystem is evolving really fast. You've got tools like Prompt Layer, which offers a nice visual interface for managing prompts, tracking their history, and comparing performance. It's quite good for collaboration, even involving less technical team members. There's Langsmith, which, as the name suggests, integrates very tightly with the LangChain framework. It gives you incredibly detailed tracing and debugging capabilities for complex AI chains, plus cost tracking, which is super important. You have Agenta, which is an interesting open source option aiming to be an end-to-end platform for the whole prompt engineering lifecycle, from experimentation to evaluation and deployment. And tools like Helicone are really focused on that production monitoring aspect. Debugging issues in live systems, setting up automated regression testing for your prompts, tracking costs and performance over time. It's becoming a proper toolkit.
Okay, so bringing a lot of these threads together, needing up-to-date info, structured outputs, reliable performance. One really common and powerful architectural pattern that addresses many of these, especially that knowledge cutoff problem for our customer agent, is retrieval augmented generation, or RAG.
Absolutely. RAG is, I'd say, almost the canonical pattern now for building production-grade LLM applications that need to leverage external or private knowledge. If you think about it, it directly tackles that frozen knowledge issue. It enhances the LLM by allowing it to first retrieve relevant information from an external source, your specific documents, databases, whatever, and then use that retrieved context, along with the original question, to generate a much more informed and accurate response. Gives the LLM access to current specific proprietary data it wasn't trained on. And a typical RAG pipeline involves usually 5 main stages. First is loading, getting your raw data in from wherever it lives, PDFs, websites, databases, APIs. Then indexing, breaking that data down into manageable chunks and converting those chunks into vector embeddings. These are basically numerical representations that capture the semantic meaning of the text. Third is storing, putting those vector embeddings into a specialized vector database, which is optimized for finding the most similar vectors very quickly. Fourth is querying. When a user asks a question, you convert that question into an embedding too, and then use the vector database to find the stored chunks whose embeddings are most similar, most relevant to the question. And finally, generation. You take the original user question and the relevant chunks you just retrieved, bundle them together into a new prompt, and feed that to the LLM. The LLM then synthesizes an answer based on both the question and the provided context.
That makes sense. Retrieve first, then generate. Now, I've heard people talk about a RAG trilemma when it comes to actually choosing the framework or library to build this pipeline. What exactly is that trilemma, and how should developers think about it?
Yeah, the RI trilemma is a useful way to frame the strategic choice you make when picking a development framework. It highlights a fundamental trade-off. You're generally balancing flexibility, focus, and optimization. It's hard, maybe impossible, for one framework to be the absolute best at all three simultaneously. So let's take LangChain. LangChain is like the Swiss Army knife, the versatile orchestrator. Its strength is flexibility. It has a huge ecosystem of integrations, components for all sorts of tasks beyond just basic RAG complex agentic workflows, tool use, custom logic. You typically choose LangChain when you need to build complex, potentially multi-step applications where R might be just one part of a larger system, and you need that maximum flexibility and control over every piece.
Okay, so LangChain for broad flexibility. What about the others?
Then you have Llama Index. Think of Llama Index as the specialized data connection hub. Its strength is focus, specifically on streamlining the data ingestion, indexing, and retrieval parts of RAG. It provides highly optimized pipelines just for building robust RAG applications, particularly for search and question answering over your documents. You choose Llama Index when your primary goal is RAG, and you want a framework that's really fine-tuned and simplified for that specific task, offering perhaps better performance or ease of use for RAG compared to a more general framework.
Focus on RAG itself. Got it. And the third part of the trilemma, optimization.
Right. And this leads us to DSPy. DSPy represents a really interesting, maybe even forward-looking approach. Its strength is optimization. DSPy isn't just another library of components. It's a framework built around the idea of programmatically optimizing your entire LLM pipeline, including the prompts themselves. It kind of shifts the paradigm. Instead of you, the developer, spending hours manually tweaking prompts through trial and error, DSPy asks you to define the overall architecture of your system, the program, and specify how you'll evaluate its performance, the metrics. Then DSPy's compiler tries to figure out the best prompts and even fine-tune smaller models automatically to maximize performance on your metrics. You'd choose DSPy when top-tier performance and reliability are paramount, and you want to move beyond manual prompt crafting towards a more systematic automated optimization process. It's arguably a more advanced approach, treating the LLM interaction less like talking to it and more like programming it, letting the framework handle the low-level tuning. It's about engineering the system to find the best prompts itself.
Wow. Okay, that was quite a journey from just asking better questions all the way to programmatic optimization of entire reasoning systems. It really feels like we've seen prompt engineering solidify into a proper formal engineering discipline. It's grounded in systematic design, that crucial iterative refinement loop, and importantly, robust data-driven ways to actually measure success. It's definitely a world away from where things were just a short while ago.
Indeed. And you see the role of the developer changing too. It's less about being a master wordsmith trying to find the magic phrase, and much more about being a prompt systems architect, someone who designs, builds, and optimizes these entire systems that are increasingly capable of generating, refining, and even self-correcting their own prompts and lines of reasoning. And if you look just a little bit further ahead, you can already see the next wave forming. Things like adaptive prompting, where the AI might adjust its own prompts on the fly based on the conversation or task context. Multimodal prompting is huge, orchestrating not just text, but images, audio, video inputs, and outputs seamlessly. And we're starting to see the formalization of prompt pattern libraries, basically, reusable, documented solutions to common prompting problems, much like design patterns in traditional software engineering.
So it seems like mastering prompt engineering, ultimately, it isn't just about getting better answers from an AI. It's really about mastering the interface to intelligence itself. Something to think about.